Then why do you want to solve?
So just to see if my answer is correct because
Your
I'm
answer
not
will be
sure.
correct. You have to tally with others. You have to satisfy material balance.
Yes, sir. So in question three, most of them got the same answer, but in question four, we are getting slightly different answers.
Yeah, sorry, I just got locked out. Yeah, Amrapali. So, how different are the answers?
So like 0.71, 1.34
Sure. Okay. Anyway,
in the range of 0 and 1.5.
okay. Anyway, let us try to see, because anyway, other people will also have some doubts, even though people may not ask. Okay. So, are you able to see the screen?
Yes, sir.
Yeah.
Yes,
Great.
sir.
So we'll start solving from problem three onwards, because problem two is just a sort of similar version of problem three. Right. So let's try to see the solution of problem three, and once we come to problem number four, um, I will answer Pravin's doubt as well. What is a good source of Antoine constants? Okay, so first of all, ambient air, we want percent relative humidity, and we want kgs of water vapor per kg of dry air. We need to find out these two things. So this is fairly straightforward. So what is given? Total pressure is 740 mm Hg, temperature is 45 degrees centigrade, dew point is 35 degrees centigrade. What does that mean? What does dew point mean? Let us recall that from the previous lecture. Dew point means if I take this air and cool this air at 35 degrees centigrade, one drop of water will appear. That means at 35 degrees centigrade, whatever is the vapor pressure at 35 degrees centigrade, partial pressure will be the same as that of the vapor pressure at 35 degrees centigrade. That means this ambient air, the partial pressure of water vapor must be such that it is equal to the vapor pressure at 35 degrees centigrade. So if you find vapor pressure at 35 degrees centigrade, what is the value from Antoine constants? Somebody can tell me the value. I'm not going to solve, since you would have already
41.67.
solved. What is the value?
41.6.
42.01.
Okay, so 42.01 mmHg. That means this particular ambient air, the partial pressure of water vapor in this ambient air having temperature of 45 and total pressure of 740 mmHg, the partial pressure of water vapor in this air is 42.01 mmHg. Right. So now what is now percent relative humidity? So percent relative humidity is partial pressure of water vapor in the air divided by vapor pressure. This vapor pressure is at what temperature? This vapor pressure, it is describing the air. It is describing how much water can this air hold if it was completely saturated. So this vapor pressure we need to find out at 45 degrees centigrade. That because at 45 degrees centigrade, the maximum amount of water vapor that can be held by that air, or that can be accommodated in that air, is corresponding to vapor pressure at 45 degrees centigrade. So percent relative humidity is partial pressure upon divided by vapor pressure at the temperature of the air. Temperature of the air is 45, so partial pressure is 42.01. Vapor pressure, somebody tell me vapor pressure at 45 degrees centigrade.
71.79.
Okay, 71.79. Of course, it is percent. relative humidity. So I need to multiply this by 100 and this by 100. So this will be around 70%, right? Some maybe 60%. What is the value? Somebody has calculated.
58.53.
Okay, 58.5%. Okay. Next, we want kgs of water vapor per kg of dry air. Right? How do we get that? So suppose I take 1 mole of the air. Now we can calculate. We have seen that mole. We have seen this last time. Moles of water vapor divided by moles of dry air. So let me again repeat. This ambient air is going to contain nitrogen, oxygen, argon, carbon dioxide, helium, whatever else, whatever else you want. Okay. Right now, just to simplify, we are saying it is going to contain only nitrogen and oxygen, and it is going to contain water vapor. So ambient air is consisting of all these things, all the components. For simplicity, we are taking 79 and 21 nitrogen and oxygen. All these non-condensable gases, means which cannot be condensed, these form our dry air. Dry air means without the water vapor. So anything else that is without the water vapor, we call it as dry air. So just like we were talking about compositions on dry basis, right? Means the moisture free basis, the water vapor free basis. Okay, so moles of water vapor per mole of dry air. That's, we have seen this in our last class. How to calculate that? That will be partial pressure divided by total pressure minus partial pressure. So this would be 42.01 divided by 740 is the total pressure. 740 minus 42.01. Somebody tell me this number. Somebody tell me this number. Is anybody around?
So 0.06.
0.06. Okay, thank you, Soumik. So if you want, it can be in terms of gram moles or it can be in terms of kilomoles per kilomole. So now we want kgs of water vapor per kg of dry air. So that would be nothing but 0.06, the kilomoles of water vapor per kilomole of dry air, multiplied by molecular weight of water vapor and molecular weight of air. We saw that 28.84. So how much is this number?
0.037.
0.037.
0.037. Thank you. Thank you, Gauri. Okay, so we've got everything here on the left side. Now this air, we are going to heat isobarically. Isobarically means the total pressure is going to remain the same. Iso bar means constant pressure. Okay, so our total pressure is going to remain same, 740 mm Hg. Now we are heating this 45 degrees centigrade air. We are going to heat it up to 80 degrees centigrade, and we want to calculate these two things. So reason we are going to heat this air is because this may be used for drying. You remember we did some calculation for dryer when we were doing crystallization, filtration and drying problem. So one of the ways in which we dry something is to allow it to come in contact with hot air. So the way we would generate this hot air would be to take the ambient air and heat it up to whatever temperature we want. In this particular case, let's say we want to heat it up to 80 degrees centigrade so that it can go to some kind of dryer. We'll do those calculations again slightly later, maybe after some time, after we finish all these two problems. But right now I just wanted you to find out what is the percent RH and what is the kgs of water vapor per kg of dry air, same way. So now what can you say about this air that is going out? Is any water going to condense out of this air by heating? Is there any water that is going to condense out of this air?
No, sir.
No, sir.
That means water is going to remain the same as water vapor. Air is also going to remain the same as air. Only thing is it will be at a different temperatures. It will be at a different temperature now, 80 degrees centigrade. So kgs of water vapor per kg of dry air is going to remain the same. That would be 0.037. Or if you want kilomoles of water vapor per kilomole of dry air, that would be 0.06. Right? If kilomoles of water vapor per kilomole of dry air is 0.06, that we already know, partial pressure divided by total pressure minus partial pressure, that's kilomoles of water vapor per kilomole of dry air, that is going to be 0.06. In other words, what we are saying, so if you look at this, you will have partial pressure of water vapor to be, what was the partial pressure? 42.01 mmHg. So what has happened is, just by heating, we are not changing the composition of the air. Whatever was the composition, that same composition is going to remain here as well, because liquid water is not condensing out, right? So if the composition remains the same, partial pressure will also remain the same. And if partial pressure remains the same, now relative humidity, will it remain the same? If partial
No,
pressure, no, why not?
this
But
temperature
Because
of
the
when
vapor
ambient air
pressure is
is
changing.
Correct.
changing.
Temperature is now 80 degrees centigrade. So the maximum possible amount of water vapor that this air can hold will correspond to vapor pressure at 80 degrees centigrade. So somebody tell me, what is the vapor pressure at 80 degrees centigrade?
355.31.
355.31.
355.
355.3 mmHg. So now the percent relative humidity would be 42.01 divided by 355.3 multiplied by 100. It will be much less than this 60% or whatever value we had.
11.8.
Yeah, 11.8. So right, so okay, let me write that. Oops, 11.8%. So now you see what has happened, because the composition has remained the same, partial pressure has remained the same, humidity has remained the same in terms of moles, in terms of kgs per kg, that has remained the same. But because the temperature has changed, the ability of water to hold, ability of the air to hold the water vapor has gone up tremendously, because it is as per vapor pressure, and therefore vapor pressure has gone up from what was the value at our whatever 35 degrees centigrade. Now it is gone up to 355, and now the relative humidity has reduced to 11.8%. Do you agree? And that's how we supply air to this dryer, this hot air containing very little moisture in terms of percent relative humidity, and that's how it is able to pick up moisture from wet solids. Okay, we'll do that calculation after some time. Okay, any question, any problem, any difficulty so far? Can we go to the next problem? Can we go to the next problem?
Yes, sir.
Yes, sir.
Okay, so the first question that Praveen was asking is, what is a good source of vapor pressure of various components? Okay, so there are a couple of good sources. there is a book called as Handbook of Chemistry and Physics. Not chemistry and physics. That has a good source of data. There is something called as Perry's Handbook of Chemical Engineering, or Perry's Chemical Engineer's Handbook. Okay. There are NIST databases that will give you a good source of Antoine constants. But for components which are very common, like methanol, ethanol, all these very commonly used compounds, many sources will give the values of vapor pressure. For each component, for each substance, let's say, each chemical, if you like, for each substance, there are something called as material safety data sheets, and different people make these data sheets, but these material safety data sheets also gives data about vapor pressure. At the most, they may give you vapor pressure at 2-3 different values, from which you will have to calculate your A, B, and C values in the Antoine's constant. But many of these sources, they will directly give you the Antoine constants. There is one more way of correlating vapor pressure. Remember Antoine constants, we talked about Antoine equation, and Antoine equation was like ln Vp is equal to A minus B over T plus C, correct? But there are other equations as well that correlate vapor pressure, and one of them is called as Wagner equation. You will see about that in the thermodynamics course. We are not going to do that just now, or we are not going to look at just now. In this course, we are only going to look at Antoine equations. But yes, there are many good sources, and for commonly reported compounds or commonly used compounds like methanol, all of these correlations that you find will be equally valid. So Praveen, can you tell us one correlation that you found?
Or like the value of A, B, and C.
Yeah, you tell us the correlation.
Sir, wait a minute.
Otherwise, I will give you another correlation. Okay, let me show that. I will just open that document. If you just do Google Antoine constants, you will get this kind of document. I will just open that and show.
Sir,
Yeah,
so can ABC be negative?
yeah. I mean, if you're writing correlation as A plus B, the B will be negative. If you're writing temperature in Kelvin, then C will be negative. How does it matter
Yes.
whether it is negative or positive? You use the proper correlation, na? If I'm
Yes,
writing it
sir.
as A minus B over T plus C, then B will be positive. If I'm writing temperature in degrees centigrade, C will be positive. So this correlation, you have to be careful about two things. One, you have to be careful about is what are the units? What are the units of temperature and what are the units of vapor pressure in which that correlation is made? The temperature that you have to give, is it in terms of degrees centigrade? Is it in terms of Kelvin? The vapor pressure, is it in terms of mmHg, Pascal, bar, kilopascal, psi, whatever is the pressure unit, right? So you have to be careful about the units, and you have to use proper correlation with the proper units. If you are having correlation of ABC in terms of some other units of temperature and pressure, and you use it for some other values of ABC, that will not work. Second thing you have to be careful about is whether it is log to the natural log of vapor pressure, or it is log to the base 10 of vapor pressure. So constants are reported for different sets of units, or either you take natural log or log to the base 10. So Praveen, when you have found 3-4 different correlations, you have to see what is the correlation for, what are the units, whether it is natural log or log to the base 10. Let me just share one sheet with you. Okay, let me stop sharing this. Let me share this sheet. 1 second. Yeah. So this is one set of Antoine constants of vapor pressure that are reported. Are you able to see the screen?
Yes, sir.
Yes, sir.
Yeah. So if you see this, it is downloaded from Google. This is compiled by Iranian chemical engineers website. Okay. Now look at this. What are they doing? Their Antoine correlation is in terms of log to the base 10, A minus B by T plus C. P, that is vapor pressure, is in mmHg and temperature in degrees Celsius. Do you see that? So these correlations, A, B, C, the values that are there, they are to be used with this set of units. So if I am talking about methanol, from this data set, it is log to the base 10 vapor pressure in mmHg is equal to A minus B divided by T plus C, and this temperature is in degrees centigrade. So they are telling us that this correlation is with log to the base 10, and it is in pressure is in mmHg and temperature in Celsius. Do you agree with that? Are you able to see?
Yes, sir.
Yes, sir.
Okay, so now we go down. So there are about 212 pages in this document, right? Which means there are lot many compounds, right? So if you see, there are about 5,000 compounds whose Antoine constants are given. Okay, so we will have to look through this. We will have to look at methyl alcohol or methanol, whichever is reported. They seem to be doing it by IUPAC method. So we need to look at methyl alcohol. Yeah. So this is methyl alcohol. Entry number 3375. Are you able to see? Yes, no.
Yes, sir.
Yes, sir.
Okay, so this is saying that A, this is the A value. So look at the first row of the table. This is the molecular formula: A value, B value, C value, the minimum temperature and the maximum temperature at which it is in between this temperature that the correlation is applicable. If you say, for example, if I am talking about acetaldehyde, the correlation, these constants A, B, C are valid from minus 123 degrees centigrade to 187.85 degrees centigrade. If you are using it for maybe 200 degrees centigrade, it will not be so accurate. So they are telling you that within this temperature range, these constants are applicable, or these constants are fairly accurate. Okay, so let's go down to methanol. Methanol was some 3,000 something. So this is something that you have to get used to. That don't think that it's not a JEE exam that everything will be given to you and you just have to plug in the formulae and get the answer. Finding the information is equally a important aspect of our functioning in this profession. So if you want to be if once you start working in the industry or once you start working somewhere, you will not be given everything. It is not a school that there will be a prescribed textbook by the Maharashtra state government or some state government and everything will be given in that, and whatever is there in that, only that much will come in the exam. Everything is part and parcel of your syllabus. Finding information also is an important aspect of education. So if you look at methyl alcohol now, these are the ABC values. Okay, let's try to see if we can copy them. I don't know if we can copy them. Anyway, it doesn't matter. We can always write 8.09126. So this A value is 8.09126 minus B. B value is 1582.91. 1582.91 temperature, and now in degrees centigrade, and the C value. C value is now 239.096. 239.096. Okay. Okay. So let's go back to our calculations. Let's see that sheet. Praveen, does that answer your doubt?
Yes, sir.
So you must be having 2-3 different values, but they may be in different sets of units.
Okay,
So you
sir.
have to be careful what you are using. Okay, so are you able to see the screen now? So I've just written the Antoine equation. I have written the ABC values here. Okay. Okay, can we go forward now? Can we solve this problem? What was the problem? Problem was we have a nitrogen and methanol coming in. Pressure was 760 mm Hg. Temperature was 60 degrees centigrade. kgs of methanol per kg of nitrogen was 0.5. We wanted to condense out liquid methanol, and we wanted to condense out 90% of methanol. Okay. So anybody would like to volunteer to do this problem? Any volunteers?
So,
Yeah.
could I?
No,
May I?
no. You are always answering. I want people who have not answered. Volunteers. Otherwise, I'll have to pick on somebody. Some people are leaving the meeting because I might pick on them. 4 people have left the meeting because I might pick on them. Oh, people are leaving the meeting. Is it because you're scared or what? Anyway, people have left. How will they answer? Edith, can we have you answering? Edith, would you like to volunteer?
So I didn't finish this one.
Okay, but even
I
if you
got
didn't,
stuck.
you got stuck, but doesn't matter. You can tell us where you got stuck, and you can tell us where you started, how you started, and where you got stuck, so we can take it from there. We can start our discussion from that point. Would you like to tell us how you got started? It doesn't matter. You might be stuck. It doesn't matter. Many people will be stuck at many places.
Sir, can you give me 2 minutes?
Yeah, yeah, sure. Take your time.
Okay.
Yeah, are you ready?
Not yet.
Okay. Okay, so Edith, what we'll do is I will get started, but you help me out with the calculation. Is that okay?
Yes, sir.
Okay, so we want to find out what temperature we need to cool so that 90% of the incoming methanol will be liquefied, and then we can separate out liquid methanol, and then the rest of the nitrogen we'll do something with that. Okay, we'll see that little later. Okay, so shall we take some kind of basis to do all these calculations? What basis would you like, Edith?
1 kg of methanol.
1 kg of
Methanol.
1 kg of methanol you want in the incoming gas or the outgoing gas?
The incoming.
Incoming gas. So okay, so our basis is 1 kg of methanol, right? So let's try to make our tables. This is going to be our condensation process, where we are going to condense or cool. Condensation, cooling. Condensation is when we are talking about condensing something. So in this stream we are going to have nitrogen, we are going to have methanol. This is a gas stream. What is the temperature? 60 degrees centigrade and 1 atmospheric pressure. 60 degrees centigrade, total pressure is 760 mm Hg. Now here also total pressure is 760 mm Hg. Temperature we don't know. This stream also is going to contain nitrogen and methanol. Okay, and then liquid methanol is going to condense out, and we are going to separate that liquid methanol. Okay, so if our basis is 1 kg of methanol in the incoming gas, right? I want to let us write this in terms of kgs. So I have 1 kg of methanol, that is my basis. And what are we told? We are told that kgs of methanol in the incoming gas per kg of nitrogen is 0.5. That means kgs of nitrogen that are coming in would be 2 kgs. Okay. Now, if
Yes, sir.
kgs of nitrogen are 2 kgs, now in coming in are 2 kgs. If I take this as a control volume, nitrogen is coming in, no nitrogen is going out in the liquid stream, only the nitrogen is going out in this gas stream. So the kgs of nitrogen that are going out is going to be 2 kgs. Right. Now we want
Yes.
to condense how much methanol? 90% of the methanol we want to condense in the liquid form. That means this liquid methanol, if I write in terms of kgs, we want it to be 0.9. And therefore, for this red control volume, we will want this methanol going out in the gas to be 0.1 kg. Is that okay? So
Yes,
far,
sir.
so good.
Mm-hmm.
Right. Now, we need to find out temperature, right? So this has this gas stream that is coming in, that has been cooled and the methanol has been condensed. Okay, so this remaining gas, this gas must be having 100% relative saturation with respect to methanol. Do you agree with that?
Yes, sir.
We did some calculations in the in the first lecture, or morning lecture of Tuesday. We calculated things condensing out, right? Do you recall that?
Yes, sir.
And then the remaining air was 100% relative saturation, relative humidity. When we talk about water and air, we talk about humidity. When we are talking about any other substance, we don't call it as humidity, we call it as just relative saturation, or saturation and relative saturation. So in this particular case, now this gas going out must be having 100% saturation, relative saturation, with respect to methanol. So that means we will need to calculate things like partial pressure, vapor pressure. This condition means at this particular temperature, the partial pressure of methanol would be
Is equals
corresponding
to
to the vapor pressure
vapor pressure.
at this temperature, isn't it? So now we need to calculate
Yes.
partial pressure. So if you have to calculate partial pressure, what do we need to calculate? Mole fraction, right? So if I want to calculate mole fraction, I will need to convert this into kilomoles. So if I have to convert to kilomoles, 2 kgs is how many kilomoles? 2 divided by 28 molecular
28.
weight of nitrogen, and kilomoles of methanol would be 0.1 divided by molecular weight of methanol. What is the molecular weight of methanol?
Certitude.
32, right? Right. So how many kilomoles of nitrogen are there? 2 divided by 28.
0.071.
0.071. How? What is the kilomoles of methanol? 0.1 divided by 32.
0.003125.
Okay, 0.003125. Okay, we can round off. We can simply say 313. What is the total? Plus 0.28.
0.007413.
00 or only 10?
10.
Yeah,
7413.
7455 something. So 746, shall we say?
No, 7413. So,
Yeah, so we are just
one.
adding 7413. So I'll just say 7413. Okay.
Yes.
So that is the total. What is the mole fraction of methanol? Mole fraction of methanol would be 0.00313 divided by 0.07413.
0.042.
0.042. So now what is the partial pressure of methanol? Would be the mole fraction of methanol multiplied by total pressure. So that is 0.042 multiplied by total pressure. What was the total pressure? 760.
31.92
31.92 mmHg.
millimeters of mercury.
Right, very nice. So if this is the partial pressure of methanol in this air, that means the temperature should be such that vapor pressure of methanol at this temperature, gas temperature T, whatever is this gas temperature T, at this particular temperature, vapor pressure must be the same as 31.92. So let's use our Antoine equation. It is now log to the base 10. Vapor pressure now is 31.92. All we have to do is calculate temperature from here. Did you get the answer, Edith?
Almost.
Yeah, okay. I have not mucked up the answer. I have just solved just now. Anyway, you solve. We'll wait till you solve.
Okay. One point zero five three.
Yeah, 1.2053. Temperatures we can't measure to third decimal place, so we'll just round off.
Okay.
Okay. Okay, so does that answer your doubt? Wherever you are stuck at?
Yes, sir.
Most important point is select a basis. You've already done that, so you just have to go through all these calculations. Okay, shall we go to the next problem? Anybody has any other doubt? Shall we go to the next problem? Anybody has any doubt?
Yes, sir.
Okay, so here is a problem. What I was describing, that we are heating the air. Remember, in the previous problem we were heating the air, and the reason we were trying to heat the air is because we want to send that air to some kind of dryer. Okay, so it is actually a continuation of problem number 3 to a dryer. So we are going to look at now a dryer, and we are going to do some kind of calculations for this dryer. I will ask you some kinds of things. So let's say there is a process dryer, and let's say something that we are drying. Let's say we are drying milk. Okay, milk, if you dry, what do you get?
Milk powder.
Yes. So we are going to make milk powder by drying this milk. Now milk contains so many things. It will contain protein, it will contain calcium, it will contain lactose, so many other sugars it will contain. It will contain what?
Fats.
Pardon? Fats it will contain. Yes, right. So we are going to say that this milk contains two things. One is the solids, which are now actually dissolved, and water. Okay. So these solids are all the calcium, lactose, fat, protein, all of those things, right? So we should just say simply soluble matter. Okay. So let's say the soluble matter is 15 weight percent, and rest is all water. We are simplifying the process. We want to evaporate the water and get milk powder. Okay. So milk powder will have now solids. That's why we were going to call this as soluble matter, or we were going to call this as dissolved solids. The solid components are dissolved in the water. Actually, it is not completely dissolved. It is in an emulsified form. So for example, fats, whatever fat component is there, that is not actually dissolved in water. It is emulsified in water. And there are natural emulsifiers, which are proteins and some sugars. So, but right now, let us not worry about that it's an oil in water emulsion, all those things. Let us not worry about that. Let us say all those components are like a dissolved solid. So once you make a milk powder, you're going to have solids, and you're also going to have some amount of water. We are not going to evaporate complete amount of water. So let's say the water content is like 0.5%. Okay, and to do this drying process, we are supplying hot air. Okay, so let's go to problem 3. That problem 3, we had a hot air coming out, right? It was 740 mm Hg and 80 degrees centigrade, right? So let's say total pressure is 740 mm Hg everywhere. That means all streams will have 740 mm Hg pressure. This temperature was 80 degrees centigrade, and this percent RH was, what was the value? 11.8%, right? This 11.8%. This hot air is going to this dryer, 11.8%. Okay. Now, so what this hot air is going to do is going to pick up part of the liquid water, because partly we still want that liquid water here. How is it going to evaporate the water from the milk? It is going to evaporate the water from the milk by providing heat to that milk. That's why we need this hot air to be at a high temperature. Okay. So whatever air comes out of the dryer, now it will be cooler. Temperature will be less than 80 degrees centigrade. And what can we say about the humidity of that air, or relative humidity of that air?
So
It
we
will
can assume
increase.
100%.
Right. It will increase, right? So relative humidity will be obviously more than 11.8%, and temperature will be, temperature will be less than 80 degrees centigrade. Okay, less than 80 degrees centigrade, more than 11.8%. Okay, I'm just going to tell you some values. Okay, so let's say the air cools up to, let's say, 50 degrees centigrade. And what is the maximum possible relative humidity is going to have? 100%,
100%.
right? So, but okay, it may not go to 100%. Let's say it goes up to 90%. All right, so the air coming out will be cooler. It will be at a temperature, let's say 50 degrees centigrade. Relative humidity will be more. Let's say it is 90%. Okay, does that is that okay? Can we go to the next problem? Yes, no?
So, sir, pressure would be 740, right?
Yeah, we are
mmHg.
we are going to assume that right now this drying operation is done at constant pressure, isobaric. Actually, there will be a slight difference between this pressure and this pressure, but let's not worry about that just now. We will do those kinds of things in semester 3. But okay, so let's assume that pressure is going to remain the same, 740 mm Hg. Okay, so let's say we want to process, let's say, 1000 kgs per hour of milk. Right? That means this incoming milk, we want it to be having flow rate of 1000 kgs per hour. What I would like you to calculate, okay, volumetric flow rate of incoming air. Okay, I want you to calculate this in meter cube per hour. Second, I want you to calculate volumetric flow rate of incoming air, hot air, but nm cube per hour, which means volumetric flow rate referred to at 0 degree centigrade and 1 atmosphere absolute pressure. Okay, these two are you clear about what we are meaning by these two? One is the actual flow rate and one is the flow rate which is referring to at 0 degree centigrade and 1 atmosphere absolute pressure. Is the problem clear to everybody? What is to be calculated? Is the problem description clear to everybody? Yes, no?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
All right, so solve now. And we need a volunteer to solve this problem. So somebody be ready. Somebody volunteer. I don't want to pick on people. Because last time I said I will ask somebody to calculate. 5 people left the meeting. I don't know whether they came back. See, now also Prathamesh Khandekar left the meeting. Is it because they left because of the problem, or is it because they left because of internet problem?
Uncertainty, sir.
Perhaps. Either they left because of MEBC, Ashish Saket Chand has left the meeting. They left because of the MEBC problem or internet problem, some problem or the other. The reason I'm taking this hot air is because you already have the values of things like humidity, kilomoles of water vapor per kilomole of dry air. All those things are there from this problem. So use those values so that we don't have to do the same calculation again and again. Or perhaps I should have changed the temperature and relative humidity. That way you could have got some more practice. Anyway, doesn't matter. Okay, so calculate. I think people are leaving and joining also. I think Google just doesn't tell that they have joined. Google tells only if they have left. The material balance is the same. We had 65 people some time back. Now also we have 65 people. So material balance is satisfied. So that means whoever is leaving is rejoining. Any answers so far? Anybody is stuck? Anybody needs hints? Anybody around in class?
Yes, sir.
Yes,
So,
sir.
Okay, okay. You're around. Nice. Anybody stuck? Anybody wants hints?
for hot air at temperature 50 degrees Celsius, it would be 27.13 meter cube per hour.
No, I want incoming hot air.
Uh,
Incoming hot air is
yes,
80
sir.
degree.
Incoming hot air. Incoming.
Okay, but
Oh,
I thought you
okay.
said 50
One
degrees
minute, sir.
Celsius.
1 minute, sir.
Yeah, yeah. Okay.
The incoming is 2.83 meter cube per hour.
Actual, not NMQ.
Yes, meter cube per hour. Sir.
This first one or second one?
First one.
First one. Two 2.83.
So for incoming hot air
Hmm.
meter cube per hour, I'm getting 29.65 meter cube per hour,
Okay.
and for normal, it would be 22.33 meter cube per hour.
So for standard, sir, n meter cube is 1.82.
Atharva, check your calculations. Something is wrong.
Okay, sir.
Perhaps gram mole and kilomole. Or maybe you calculated per kg or something like that. Any other answer? Any volunteer to solve this problem?
Sir, it should be actually 22.33 into 10 power 3. I made an error of 1000.
Oops. Same way here also, right?
Yes, sir.
I got 30,330.
Which one? First one or second one?
First one.
30,000?
330.214.
I forget that point too. Perhaps I can round up both these things.
Sir, sir, I got 16,620.
16,000.
16,620. And the second answer is 22,082.
Anybody would like to volunteer, especially those who have not volunteered so far? Otherwise, I'll just have to say some random name. Prashasti, are you there? Would you like to volunteer? Prashasti is not there. Prakash, would you like to volunteer?
Yes, sir.
Would you like to volunteer with the answers?
No, sir.
No?
No.
Okay, you may not have the answers. Would you like to, after some time, would you like to tell us how you have solved?
Sir, I don't think.
You're solving or not solving? You're solving, right?
Sir, I am stuck.
You're stuck. Where? So I'm asking you, I'm asked so many times. If people are stuck, you want any hints? Where are you stuck? Prakash, can you tell us where you are stuck?
Sir, I think I can solve by.
You can solve, or you're stuck, or what are you telling, Prakash? I'm not able to understand what you want to say. You don't want to volunteer. Either what you are saying,
Yes, sir.
but you can solve.
Yes.
Then there is no point in having you as a volunteer. Prashasti, are you there? Not there? Ram, Ram Dandekar, are you there?
Sir, I just started solving. I was having my breakfast.
You are having your breakfast. All right. Why not have breakfast while solving? Nobody stops you from having breakfast, but
No, sir, one thing at a time.
yeah. So one thing at a time means MEBC problem should be the first priority.
Sure, sir, I'm solving, sir.
Are you comfortable solving, or you think you will get stuck somewhere?
I think I'll get stuck.
Arre baap. How much more time do you need, Ram?
Uh, 5 to 10 minutes.
Okay, so we'll see if there is another volunteer. Otherwise, we will ask you. Somebody who is not answered so far. Just trying to look at some names.
Sir, can I?
Nishant, you have been answering many times.
Okay, sir.
I want to involve people who don't talk in class. Dhruti, are you there? Because only way I can talk to them is if I ask them question, they will come out with their doubts. Dhruti, are you there with the answers, or you need some more time? Would you like to volunteer?
Sir, I tried.
You have a doubt.
Sir, I'm still. Yes,
So
sir.
would you like to volunteer?
No, sir, I'm still trying.
You can still try. I'm not saying that after 2-3 minutes, maybe would you like to volunteer? The other Arya, are you there?
Sir, can I volunteer?
No, Hardik, you have been answering many times.
Okay, sir.
I want people who don't talk in class. Sahil Khandelwal. I don't remember whether you answered or any time. Sahil, are
Yes,
you there?
sir.
Would you like to volunteer?
Sir, I'm still doing it.
Okay, so whatever you are still doing, can you volunteer with whatever you finished up to this point?
Yes, sir.
Great. We have a volunteer, Sahil Khandelwal. So tell us, Sahil, up to how you have solved up to this point, how you started, what did you calculate?
Sir, I find the kgs of dissolved solids and water.
Okay, right. So let us write all these answers, whatever you have calculated so far. Let us write that. So this is the basis that you have taken, right?
Yes.
1000 kg per hour of the milk. Now this is going to contain 15% dissolved solid, so that is going to be 15% of 1000. So that is 150,
150.
correct. And then water is going to be 1000 minus 150, or 85% of
850.
1000. This is going to be
850 kg.
850. Very nice. Now what did you do?
Sir, the solids remain same, so the 150
Right.
kg.
It is not kg, it is kg per hour,
Oh,
isn't it? Because it's a continuous process. Milk is coming in continuously, air is coming in continuously, air is going out continuously. Milk powder is coming in, is getting produced from this dryer continuously. So we are talking about per hour basis. So the solids remain the same, the tie component, 150 kg per hour, and this solid must be 99.5 weight percent. and therefore water must be
0.76.
point. Let's just take one more decimal place, 0.754. Let us say three significant digits. Is that okay, Sahil?
Yes, sir. Yes, sir.
Okay, now tell us, what did you do? Sahil,
Sir, I find the vapor pressure
at what temperature?
at 80 degree.
Okay, that we are already found, right, in the previous problem.
Yes, sir.
Vapor pressure at 80 degrees we had already found. Where was that? 355.3 mmHg. Isn't it? You remember the previous problem?
Yes, sir.
So this is hot air. So you found out vapor pressure, that was 350. What? 350, how much was that? 355.3. Okay, now what did you do?
Sir, I find partial pressure.
Okay, partial pressure also that we found in the previous one, and that's how we in fact found the relative humidity. Partial pressure was 42.01. It was already there in the previous problem, right? Or
Yes,
did you
sir.
do
So
this?
now,
Did you do it again?
no, no, sir.
Okay, okay. Huh.
So now mole fraction of water, hot vapor,
Mole fraction of
hot vapor,
hot vapor.
hot air,
Mole fraction of dry air.
dry air.
Dry air or water vapor, or both?
So dry air.
Okay, how did you find that?
Sorry, sir, water vapor,
Ah,
not dry air.
correct, correct. So mole fraction of water vapor. How did you find that?
Partial pressure upon total pressure.
740. Okay. What is the value? Sahil, you have solved or not solved?
Sir, I'm doing it.
Up to here you have done, or you're you have done this, or no? But now you have to do now 42.01 divided by 740.
Sir, sir, actually my answers got flipped. Actually, the upper one should be lower and the lower one should be upper.
Ah, ठीक है, that's okay.
Sir, 0.056.
568. Three digits if you want. Three significant digits. Okay, now
Sir, now balancing the water.
how do you do that?
Sir,
Well, okay, let me solve, or let me give you some hints how to solve. See, just like we have made a table here, what are the various components that come in, what is their weight percent, what is their kg per hour. Here also we should first of all write different things that come in from this hot air. What comes in is the dry air part and the water vapor part, right? If I want to write in terms of kgs of water vapor per kg of dry air, how much is that? That we already got in problem number 3, isn't it? Kgs of water vapor per kg of dry air, that was this number 0.037. Do you recall, Sahil? Problem number 3, have you solved or not solved? Sahil, are you there? Are you not there?
sir, I am there.
But why are you not answering?
Mic is not working properly.
Now it is working properly. So kgs of dry air per kgs of water vapor per kg of dry air we had already calculated. That was 0.037. So straight away we can take from here kgs of water vapor per kg of dry air is 0.037. Right? Now the air going out, again this air that is now slightly cooler, this air is at a 50 degree centigrade temperature and 90% RH. Right? So if I find vapor pressure at 50 degrees centigrade, what is the value? Somebody calculate vapor pressure at 50 degrees centigrade.
.39.
Okay, so 92.39 mmHg. Now it is 90% having relative humidity, so partial pressure must be 0.9 times 92.39. This would be
83.151.
okay. Thank you, Gauri. 83.151 mmHg. So now can we find out kgs of water vapor per kg of dry air in this outgoing air? That would be 83.151 divided by 7. What is it? 740. 740 minus 83.151. This would be kilomoles of water vapor per kilomole of dry air. I would need to multiply by 18, divide by 28.84. Then I will get kgs of water vapor per kg of dry air. Somebody tell me that. Somebody calculate and tell me.
0.079.
0.079. So now this air is going to have kgs of water vapor per kg of dry air is going to have 0.079 kgs of water vapor per kg of dry air. Now you see kgs of water vapor per kg of dry air in the incoming hot air was 0.037. Kgs of water vapor per kg of dry air in the outgoing air is 0.079. So now if I say that in terms of kg per hour, if I say I have x kgs per hour of dry air coming in, if I say we have x kgs per hour of dry air coming in, now we can write control volume across the dryer and we can write material balance for the water vapor and liquid water, right? So what material balance would we write? Kg per hour of water coming in to this dryer must be equal to kgs of water vapor or water in the liquid form or in the vapor form going out of the dryer. There is no chemical reaction happening, so water is not generated. So whatever water comes in must be equal to the same, must be equal to the water goes out. Either it will be in the liquid form or in the vapor form. So now can we write how many kg per hour? Now I will rub this out so that I can write with reference to this. Material balance for water across that red control volume. What we are going to say is kg per hour of water in liquid form or in the vapor form coming in must be equal to kg per hour of water going out in liquid form or vapor form, both the forms put together. So if we call this as, let's say, stream number 1, stream number 2, stream number 3, stream number 4, water comes in to this red control volume from stream number 1 and stream number 3. From stream number 1, the amount of water coming in is x multiplied by 0.037. from the hot air stream. Do you agree with this? Plus water comes in from stream number 3, that is the milk, that is 150 kg per hour. Water goes out from stream number 2, not 150, it is 850 kg per hour. This water goes out from stream number 2, that's 0.754 kg per hour. Plus water goes out in stream number 4. Now the dry air is going to remain the same. Whatever is the dry air coming in, same amount of dry air must be going out. That's why we do calculations on the basis of kgs of water vapor per kg of dry air. So how very simple it becomes. Water going out must be x multiplied by 0.079. So then we can find x, 850 minus 0.754 divided by 0.079 minus 0.037. Do you realize the advantage of doing calculations in terms of kgs of water vapor per kg of dry air? The dry air part is remaining unchanged. So if I write the table here for the outgoing air, this will have dry air, this will have water vapor. In terms of kg per hour, this would still be x. That's why we want to do calculations in terms of kgs of water vapor per kg of dry air. So somebody calculate x from here.
20,220.
20,220 kg per hour. Okay. So now I can write things. So this dry air, kg per hour of dry air would be 20,000. What was that value? 20,220. Let me just write it properly. Now I don't need the humidity values. I already have the humidity values, right? So the dry air coming in and water vapor coming in. Dry air coming in kg per hour, 20,220. Dry air going out, water vapor going out in terms of kg per hour, 20,220. Okay. What will be the water vapor coming in along with this hot air? It would be 20,220 multiplied by 0.037. Do you agree? This would be 748.14 because this has a humidity of 0.037 kgs of water vapor per kg of dry air. And the outlet air has humidity of 0.079 kgs of water vapor per kg of dry air. Do you agree with this? 748.14. The outgoing air will have 20,220 into 0.079 kgs per hour of water in the vapor form. So that is 1597.38. I can even round off. I can just say 1.1597 or 1600 if you want. Do you agree with this? Everybody comfortable so far? Anybody has doubts up to this point? Comfortable so far? Now we want volume. We want volumetric flow rate. Right? So I would have to convert this, use the gas law, but to calculate the gas law, we will need in terms of kilomoles per hour. Right? So 20,220 kgs per hour of dry air. Molecular weight of dry air 28.84. So 20,220 divided by 28.84, that will give me 701.11 kilomoles per hour. And 748.14 kg per hour of water in the vapor form divided by molecular weight, that is 18. So kilomoles per hour of water coming in would be 748.14 divided by 18. This would be 41.56. So total kilomoles per hour coming in would be 701.11 plus 41.56. That would be 742.67 kilomoles per hour. Do we agree with this? Anybody has any doubts up to this point? Yes, no? Can we go forward? Anybody has doubts?
No, sir.
Okay. So now we want to find out the volumetric flow rate. Volumetric flow rate 742.67 kilomoles per hour. So we are going to use our ideal gas law. PV is nRT, right? So volumetric flow rate would be nRT divided by P. So this would be 742.67. Write the units, kilomoles per hour. R, I can take 8.314 joules per gram mole Kelvin. But now you see, this is kilomoles and this is gram moles. Right? So I would need to multiply by 1000, or I can simply say this is R can be 8314 joules per kilomole Kelvin. And temperature. What is the temperature? We want the actual flow rate first. The first thing that we want, actual flow rate. Temperature. What is the temperature of the incoming air? 80 degrees centigrade. Isn't it? 80 degrees centigrade. That's the temperature of the incoming air. So temperature. N R temperature 80 degrees centigrade. So 80 plus 273.15 Kelvin divided by pressure. Now this is in terms of joules. So I better take pressure in terms of Pascal or Newton per meter square. So pressure is 740 mmHg. So that is 740 mmHg divided by 760 mmHg. That would be in terms of atmospheres. Multiply that by 1.0133 into 10 raised to 5. That will convert into pascals. Right? So Pascal. And then joules we can write as meter cube into Pascal. So now kilomoles will cancel out. Pascal will cancel out. Kelvin will cancel out. And we will get answer in meter cube per hour. So somebody calculate this number.
22129.3.
Let us round off. All right. So that's our first answer. Now second answer, we want volumetric flow rate, but referred to at 0 degrees centigrade and 1 atmosphere absolute pressure. So that we are going to call as N meter cube per hour. So same way, only thing is I will have to take volumetric flow rate would be 742.67, same way into 8314. Only thing now temperature would be 0 degrees centigrade. So 273.15 Kelvin, and pressure would be 1 atmosphere. So this would be in terms of meter cube per hour at 0 degrees centigrade, 1 atmosphere. So we are going to say n cube per hour. All right, so that's how you will be able to solve. Anybody has any doubts? Any place where you got stuck, where you got lost? Can we go to the next problem? Can we go to the next problem?
Yes, sir.
Yes, sir.
So I will just describe the problem. I will just describe the problem and then we will stop. Oops, so sorry. I will just describe the problem and then we will stop. Okay, so let's say we have ambient air. And let's say it is raining very heavily outside. So let's say temperature is 35 degrees centigrade, raining heavily. So percent, let me give dew point. Dew point is 30 degrees centigrade. We want to do something to this air. So now I get hot air. This is at a temperature of 80 degrees centigrade. And let's say it has percent RH of 5%. Okay. You have to figure out now, how do I, let's say total pressure, just to make your life simple, is 760 mmHg. Right? You have to figure out what you need to do to go from this ambient air to hot air at 80 degrees centigrade. Okay. So is the problem clear to everybody? Maybe you want to do just one operation, maybe you want to do two operations, maybe you want to do three operations.
Sir, can you please repeat?
Sir, please could you explain the whole problem again?
I have ambient air at 35 degrees centigrade and a dew point of 30 degrees centigrade. I want to take this air, I want to do something to it. That's what you need to figure out, what you need to do to it, so that we get hot air at 80 degrees centigrade having 5% RH. Is the problem clear?
Okay, sir. Thank
You
you.
have to figure out. You have to figure out what to do. So far I was telling you what we are doing, and then we were calculating something about the outlet or inlet. Now I'm giving you the input. I'm giving you the output. I'm asking you what you want to do in between. You may want to do one step, you may want to do two operations, four operations, 5 operations, 10 operations, whatever operations you can think about. Processes. Is that okay? In the blocks. Now is the problem statement clear?
Yes, sir.
All right. So shall we stop for the day?
Okay, sir. We have a lecture at 2:30.
Ah, oh God. Oh no. So shall we meet at 4 or what do you want to do? 4 or 4:30? What is your preference?
Sir, I guess the students are here, so they can say about it.
Yeah, other people should say. Absolutely. So your lecture is 2:30 to 3:30, right?
Yes, sir.
So it may get extended to maybe 3:45. Then we will give 15 minutes break for Ram to eat something. Otherwise, he will stop the problem and go off to eat something. Ram, 15 minutes is okay for you?
Yes, sir.
All right. So next time onwards, I'll make sure that you have had breakfast first. So 4 o'clock shall we meet?
So 4:30 would be better.
Okay, 4:30. Fine. So we'll meet 4:30. So you better solve this problem, but till 4:30. Then we can quickly solve this problem and go to the next concept.
Okay, sir.
Okay.
Okay.
Bye. Have fun.
Bye, sir. Thank you.
Bye.
Thank you, sir.
Yeah, bye. Thanks.
Thank you, sir.
Thank you,
Yeah,
sir.
bye.
Thank you, sir.
Let me
Thank you,
stop
sir.
Thank you, sir.
recording. Bye.